Now?
Yeah, yeah, yeah.
Oh my God, man. This is as all right. Okay, so
So that's a battery. Energy
okay,
storage.
all right. So do you guys have these notes in front of you? Yes or no? Do you guys know where to find it? All right, it's just all right. I'm gonna take a chance. Get out of here just briefly, just to make sure that everyone is on the same page. All right, just go to modules and then just wait. All right, so let's go to modules. Capacitance, current. All right, so current and resistance. Direct current circuits is the next lecture. Current and resistance. Click on that one, and it's going to give you this. All right, so current and resistance is going to give you the problems. All right, this time I lost everything. All right, so lecture review material is here. Just click on it. The notes that we're using is chapter 19 lecture notes. All right, so click on the chapter 19 lecture notes. It should take you to this. All right, so let's get back to this. All right, are you guys able to see this page now? All right, so Matthew says yes, so let's go forward, guys. So the first thing is a battery. This is what we were discussing. All right, so you got two opposite charge regions. You got two terminals. Okay, so two metal pieces. One is slightly negatively charged, the other one is positive charge. And notice that the electric field is pointing from positive to the negative charge within this gap. So you want to keep the electric field strength constant so that the voltage difference is constant. That's it. In order to do that, you need to keep replenishing negative charges to the negative charge region, which is the terminal. So that happens through acid solution. And now what happens when you actually when you get a wire and then connect the wire between these two terminals. Okay, so I'm just going to connect the wire between these two terminals. And this is the wire itself. So what happens, it's got electrons on the inside, right? So the electrons will experience a force in this direction due to the electric field, and they will accelerate in that direction. On top of that, put differently, when you place an electron here, when you place a net charge, it's going to have a potential energy. So the charges will become energized, and that energy turns into kinetic energy. Okay, so what that means is the charges will move in this direction from, in reality, negative charge terminal towards the positive charge terminal. All right, the motion of the charge is known as current. That's it. All right, so the current simply means that these conduction electrons are all moving in the same direction. So you get this traffic flow. That's known as current. Normally, the conduction electrons would move at random directions. If you can get them to move in the same direction, which you can by energizing them, you end up getting current. So what does that mean? That means that what drives current is the voltage or voltage difference. All right, so current density is something that we will get back to, so I'm not interested in that. All right, so let's move on to this page. It says derivation current. The current is net charge per second, the number of charges per second going across this cross-sectional area. All right, so that depends on how fast the charges are moving in this direction. The faster they are moving, the more charges will be going across this region per second. That's what it means. So the larger the net charge is, the larger the current is. The larger the net charge becomes large because the charges are moving at a given speed. So faster they move, the larger the net charge, the more the current is. And the junction rule, we didn't really discuss it per se. It was fairly commonsensical. So the current comes in, so the number of charges that are coming in here, there's a junction here. So part of the current is going to flow this way, part of the current is going to flow that way. This is known as the junction. All right. The current coming into the junction and the currents leaving the junction will add up to zero. All right. So this is known as the junction rule. This is based upon the conservation of net charge. Net charge is conserved. So the net charge going in and coming out of a junction is going to be zero. So the total current going in and coming out is going to be zero. If it's going into the junction, that's taken to be positive. The currents leaving the junction will be negative. So that's how you sum them up. All right, so I didn't really emphasize yesterday because it wasn't that important. What's important is the tiny little discussion that I had here, and then I'm having the same discussion here, and I'm looking at it. The explanation is a little bit off, but I'm fine with it. Okay, so what's happening is, so you got the two opposite charge regions, all right, and you are maintaining a constant voltage or potential difference because this is part of a battery. All right, so it's going to give you a constant electric field in this direction, and there's a separation distance, so which means that there's a voltage difference. You keep it constant. Q here represents all these dots, the net charge that you're looking at. The net charge here is going to be negative, so all these charges are energized. Or because they're inside, it says under a constant force field, which is correct. The reason why this is correct because these two things are going to act like parallel plate capacitors. So it's going to give you a constant electric field, and we know that how? Because the charge density is going to be uniform. Surface charge density divided by epsilon naught is going to give you a constant electric field. An electric field acting on the charges will induce a constant force, and constant force is going to cause a constant acceleration. So within this region, the motion is predictable. I mean, ignoring the resistance, everything is 100% predictable within this region. So what happens? because we're dealing with a conservative force field, charges are energized. So what happens, as soon as you connect the wires to these terminals, all these charges become energized, and these charges are free to move. As the potential energy goes down, it's going to turn into kinetic energy. And motion of these charges are known as the current. So all this blah, blah, blah lands us right here. So what drives current is the voltage potential. Resistance is going to slow down the charges. So the traffic flow is going to slow down. All right. So the current is what drives, voltage is what drives current, and resistance is what diminishes it. All right, so this is the general setup. Once again, this is your voltage supply. R may represent the overall resistance of the wires, or it could be an appliance that you put in as some kind of a resistor that you put into the system to actually regulate the current itself. All right, so the guy who puts these two facts together, his name is Ohm, so this is known as the Ohm's law. All right, guys, one of the things that I want you to know in terms of the future multiple choice questions. This is a linear equation. All right, this is a linear equation. I'm just going to write this out and then. All right, just write it out as a linear equation. This is going to give you the slope. All right. Resistance is going to be the slope, and it's going to be linear. What that means is, in the Ohm's law, the resistance is not temperature dependent. Okay, so just remember that. If you're using some kind of a resistor in this case, the temperature dependence is kind of ignored. I want you to just remember that. So the resistance is not temperature dependent in the Ohm's law. All right, so there's going to be a multiple choice question. When you get to it, just remember. All right, overall, there's going to be resistance is going to increase with temperature. Usually increases very little, but Ohm's law assumes that the resistance of a resistor is going to be temperature independent. All right, so that's one of the assumptions that I want you to remember. Overall, though, here's what you get. What does resistance depend on? So it's going to depend on the resistivity of the material. So the resistivity is related to the atomic structure. So how much the atomic structure resists the motion of these charges. So we get to use the letter rho for that. The other thing, it depends on the length of the wire. So the longer the wire is, the more the resistance is. The thicker the wire is, the smaller the resistance is. So these three facts are summarized in this formula. So this is what we end up getting. And then we know that with temperature, the resistance is going to increase. So just ignore the Ohm's law in that case. All right, so if temperature goes up, the resistance is going to go up. All right, so the reason why that's going to happen is because electrons colliding with these atoms and molecules will send them into vibration and motion. So vibration and motion simply means temperature, so temperature goes up. So when the temperature goes up, which means that these passageways, the spacing between the atoms and the molecules will become smaller and smaller. So that's simply going to increase the resistance. Now, how much that's going to increase the resistance mathematically could be illustrated in the following fashion. So obviously it's influencing the atomic structure. So what's happening is the resistivity is going to change. So how much the resistivity is going to change depends on the initial resistivity. And then it's also going to depend on change in temperature. All right, and once again, we will get to do something that I hate. We got two proportionalities, so we will get to put a proportionality constant to take care of that problem. So here's the change in resistivity, and we will turn it into an equation. So the resistivity is going to increase by the increase in temperature. It's going to depend on the initial resistivity, and then we will have to use a proportionality constant. Here's what I hate. So they usually use these Greek letters, so why not use the proportionality sign and say alpha and use that as a proportionality constant. All right, in essence, that's exactly what they end up doing. All right, whoever came up with this formula. So change in resistivity. All right, so this equation becomes that equation, and then you take this equation and then change it a little bit and express it just like that. It turns into that equation. All right, this new constant that we came up with, it's got a name. It's called the temperature coefficient of resistivity. So it's going to depend on the substance itself. And the temperature coefficient of resistivity is a very small number. I'm not going to do any math problems because it's plug and check. If you like plugging and check, just being an accountant, this is not the most exciting thing that you could do. But one of the things that you realize is the temperature, the resistivity is going to change, because the spacing between the molecules will diminish. And if the resistance changes, if resistivity changes, it's going to change the resistance. So this formula will turn into that one. That's it. Okay. You guys will be doing multiple choice test questions. Obviously, know how to use the formula. Okay, this can't be too complicated. So this week's test is going to be fairly simple and straightforward mathematical. All right, so this is one of the formulas that you will get to use. All right, so just understand the concepts. If you're interested, if you have a physics book, go over some of the example problems. All right, there isn't much going on in this chapter. All right, so the last thing that we did yesterday was the power. Okay, in terms of power, there are two things that happen. Number one, power is generated, so it happens inside the battery. So the battery is what generates the power. And the power is going to be lost through some kind of resistance. Usually use a resistor. It could be a light bulb. It could be a radio. It doesn't matter. All right, so something that's going to heat up, and if it heats up too much, it can actually turn into light, so it can glow. All right, so power loss is how fast electrical energy is converted into heat and or light. All right, so this is the formula. Larger the resistance is, the more power is going to be lost. Translated to English, larger the resistance is, more light you will get out of it, if that's your purpose. And power is going to be generated inside the battery, so how fast the chemical energy gets converted into electrical energy. All right, so this is power generated, this is power loss, and here's a compromising formula that has both of them. Compromising formula, what the hell? So this is a summary statement of both of them. All right, so power loss and power generated, instead of using these two formulas, you can also, in addition to that, you can use that formula. All right, so that's a general summary statement of everything that we've done so far. All right, 5 more minutes and then we'll go take a break. So electrical power, tungsten. Speaking of tungsten, for the incandescent light bulbs, we use tungsten today. And tungsten, take a look at the resistivity of tungsten, so it's kind of 5.6. Higher the resistivity is, the faster the electrical energy is going to turn into heat and light. In this case, it's going to light up much faster. All right, so what I want you guys to do is I want you to compare the resistivity of tungsten to iron. Why don't you use iron? Resistivity of iron is much higher, which means that for the same amount of current, you're going to end up getting a lot more light out of it. Tungsten is much more expensive. It's not as readily available. So why not use iron?
Right, so make it such a small enough wire to the point where you can use it in a light bulb.
Okay, Lucas, I'm going to give you 5 points. So you're thinking that it's a little bit more brittle, you think? Is that what it is?
Exactly. I think that if you stretch out iron to that level, what you would need for a light bulb filament, it would just fall apart.
Okay, so that's not a bad argument. So what else can you guys come up with?
Costs too much, breaks too easy.
Okay, I think iron is a lot more readily available. It probably doesn't cost as much.
It costs too much to run. The electricity you'd have to send through it would be much more costly than the otherwise. Also,
or you can make it cheaper. You don't have to run as much electricity.
Okay. You have a much higher temperature resistance, so it doesn't melt. So you can get more light out of it before it melts, or more power through it before it melts.
Yeah,
Matthew, I'm going to give you 5 points. Nathan is making a good point. So the melting point of iron is fairly low, right, compared to tungsten. So when it heats up, it's going to melt much more quickly. In fact, Edison's team actually tried this, and then they were able to get light out of iron up to 20 minutes. I think that's the maximum that they were able to run it. Okay, I tried it once a couple of years back, and my success was like 15 seconds long. So, I mean, it was really bright, but it didn't last that long because it melts very easily. Tungsten is a much higher melting point. That's the reason why it can last 20 to 30,000 hours. I mean, they tried. Edison's team tried. They tried anything and everything under the sun. Eventually, they settled on carbon filament. And I think the tungsten is something that they started using in the 1920s or so. Until then, I mean, they were stuck with carbon filament, basically.
These bulbs have a life expectancy of 25,000 hours. I'm on a roll tonight here.
A light bulb lights because its filament offers some resistance to the flow of electrons.
Okay, that looks better.
As the electrons try to crowd through a hair-thin tungsten wire, the energy spent overcoming resistance turns into heat.
A material that's resistive is one that requires some kind of work to push the charge across. That means you're giving up energy that turns into heat and will heat that element up.
And here, heat means light. The filament reaches a temperature of about 4,500 degrees Fahrenheit.
4,500 degrees of Fahrenheit. All right, guys, take a break for 10, be back within 10.